classify this as MCAT question. Okay. Now, I imagine a lot of you will probably want to go to medical school, so you will probably be taking the MCAT exam sometime in your career. So I'd like to show you a typical MCAT question. Okay. Typically, what they do on the MCAT exam is they'll ask you a biochemistry question. Okay. Now, they expect you to know the chemistry part. The biochemistry part usually is given as kind of a reading comprehension type of situation. Okay, so here's how a problem appeared on the MCAT exam one year. It had to do with barbituric acid, which is actually a calmer. It calms people down. Okay, now barbituric acid is a weak acid, and they gave you the case of A for it. So probably the first thing you want to do is write down the expression for the weak acid. So molecules of barbituric acid forming hydrogen and barbiturate. Okay, and they give you the case of A. Now, the MCAT exam, the math isn't very hard. They're interested in concepts. Okay, so they give you a nice number like 1 times 10 minus 5, and might as well at the same time take the P case of A, which is a P case of A of 5. Okay, now, any student who used the table method to answer the questions coming, it was very easy. So that's what I've kind of set up with you. Okay, so I've got the ratio of the base to the acid. I could have done it the other way, but you'll find out later why I do that. So the base to the acid, and I start off with a pH of 5. Why is that? Because that's why I know the ratio is 1 to 1. Okay, now remember how this goes. As you go to higher pHs, more basic, it favors the base. So at 6 is 10 to 1, then 1001, 101, then 1001. Going to lower pHs, it favors the acid. So therefore, at pH of 4, the acid becomes the higher concentration by 10, then by 100, then by 1,000. Okay, so here's the table. Now, the next thing they explain to you is a cell membrane. Now, you probably learned about a cell membrane in biology anyway, but they give this explanation. They say that your cell membrane is made up of a lipid bilayer. So I'm going to mark in yellow a phospholipid. Now, the lipid has a nonpolar end, I marked an N, and a polar end, which I marked in a charge. Now, your body is mainly a water system. So what happens is the nonpolar end doesn't like water. It tries to get away from that. And so what you get is you two of these phospholipids join together. It's called a lipid bilayer. So the key thing to notice is that the non-polar ends are in the middle and the polar ends are on the outside. And then you have millions of these together, and that forms the cell membrane. Now here's why this is important. Do you see chemical X? It's a neutral molecule. Neutral molecules can zip right through the cell membrane because they have no charge, so they can pass right through the non-polar end. Now look at chemical Y. I didn't mark it too well, but it's supposed to have a negative charge here. Okay. Now chemical Y having a charge cannot go through the middle of the cell membrane because the nonpolar ends repel them. But if you're curious, how could a charged chemical get inside a cell? There are these things called active transports that can actually be carrying through, but on their own they can't do it very well. Now here's why this is important. Go back to barbituric acid. So the charge part cannot go through the cell membrane very well, but the neutral part, the H bar, can pass right through. Okay, now here comes question A. Will barbituric acid go through the stomach lining faster, which has a pH of 2, or your small intestine, which has a pH of 8? So pH of 2 or pH of 8. Now here's what you want to do. You want to look at the form of barbituric acid at pH of 2. Notice it's mainly the neutral molecule. At a pH of 8, it's mainly the charged form. So let me give you a second to answer yourself. So would barbituric acid absorb through the stomach lining faster or the small intestine? Answer is the one with the neutral charge is the one that goes right through. So at a pH of 2, barbituric acid is mainly neutral. It'll go right through. And the small intestine will have a hard time going through because the charged form, which it mainly is, will not pass through. Okay, you ready for question B? Question B is, the doctor gives the patient some sodium bicarbonate, which changes the pH of the stomach from 2 to 4. Okay, question. Multiple choice question. Will this speed up the absorption of barbituric acid, slow it down, or does it make any difference? Speed it up, slow it down, or not make any difference? Okay, the answer is found by looking at the form of barbituric acid at pH of 2 versus 4. Notice at a pH of 4, you have less of the neutral form, and the neutral form is the one that goes through the cell membrane. So it absorbs faster at a pH of 2. So by giving the sodium bicarbonate, it slows up the absorption of the barbituric acid. You ready for question C? Okay, will barbituric acid dissolve in the blood? Answer, the blood has a pH of 7. So at a pH of 7, what is the form of barbituric acid mainly? Now remember, blood is mainly water. Water is polar. So anything polar will dissolve in the blood. So at a pH of 7, notice barbituric acid is mainly in the charged form. And the charged form would dissolve in the blood, dissolve in water very well. So answer is yes, barbituric acid would dissolve very well in the blood. By the way, notice how effective this blood drug would be. So you swallow the drug. What's the first thing you hit? You hit your stomach. Okay, the stomach has a pH of 2, and a pH of 2 is in the neutral form, so it'll go through the stomach lining very easily. Once it goes through the stomach lining, it runs into the blood. The blood has a pH of 7, and the form of barbituric acid changes to the charged form, so it dissolves very well. The blood can carry it, therefore, to the cells, to your brain or whatever, and therefore be very effective. So what do you think? You too could go to medical school, don't you think? That wasn't very hard. Okay, you're now ready for some swimming pool chemistry. Okay, question. What kills the bacteria in swimming pool? Anybody?
Chlorine.
Chlorine, exactly right. Okay, not quite that simple. What happens is when you put chlorine in a swimming pool, it reacts with water to give you hypochlorous acid. This is actually the killer of bacteria. Now, this HClO is a weak acid, which means it's in equilibrium with hydrogen ions and its conjugate base. Now, this is really the active form. It's HClO that really kills the bacteria. Its conjugate base is not very effective. It takes about 30 minutes to kill bacteria. So you mainly want to have this form, HClO4, if you want to kill bacteria. Now, I've given you the K sub A for this weak acid, 3.5 times 10 to minus 8. Okay. I've also given you its pK sub A. Let me see if I did it correctly. Okay, so let's see. How do you get pK sub again? So K sub A is 3.5 EE8 minus. So what's pK sub A again? Oh yeah, I take the log of it and change the sign. So I can answer 7.455. Yeah, 7.5. Okay, I got a question for everybody. What is the ideal pH for a swimming pool? If you're going to swim in some water, what would you want the pH to be? How about you? I'd like 7.0. Don't you read nice neutral water? It turns out the proper pH for a swimming pool is not 7.0, but it is 7.2. I often wondered why. I did some research. You know what I found out? pH 7.2 is the pH of your tears, your eyes. So if you swim in a swimming pool of 7.2, it'll not sting your eyes. Isn't that kind of cool? Okay, now here comes some homework questions for you. Question number 1 is, at a pH of 7.2, what is the ratio of HClO to ClO minus? Now, you can solve this problem algebraically by using the weak acid system. Okay, so you want to use the K sub A. You want to make the pH 7.2, which means you're going to adjust the hydrogen concentration. You're going to solve for the ratio of the good form to the not so good form. Okay, and I'm hoping you get I hope you get a big answer, because we're hoping at 7.2 it's going to be effective at killing the bacteria. Okay, question 2 and 3, I want you to use the table method. Okay, so you're going to set the table yourself. Start off with a pH of 7.5. That's the pKa would be 1 to 1. And what I want you to know, I want to know from you is that what pH would it be effective at killing bacteria? I want a ratio of 10 of the more effective form to 1 of the not effective forms. So I want to know what pH would you have a ratio of 10 to 1. Now, question number 3 is, Now, at what pH would it not be very effective? In other words, you've got one of the effective form to the not effective form. Okay, so these would be 3 homework problems for you. And these might be typical Berg exam questions, some of this type. So you're now experts, or you will be, at swimming pool chemistry. Okay, next slide, okay? You ready? Okay, so far we've been dealing with acids that only have one hydrogen in them. Now we're going to deal with many hydrogens in the acid, called polyprotic acids. I'm going to take you through 2 of them, and I'm going to give you a homework on a 3rd one. Okay, so the first polyprotic acid we're going to look at is going to be sulfuric acid. Well, I'm curious, when I mark things in yellow, can you see them?
Yes.
Great,
Yep.
okay, good. Okay. Now, so when you have a polyprotic acid and you look up its K sub A, you'll find a K sub A for every one of its acid hydrogens. So sulfuric acid has a K sub A1 and a K sub A2. Now, I must admit sulfuric acid is kind of unusual because K sub A1 is infinity, which means it actually acts as a strong acid for the first one, and the second one will have to be a weak acid. Okay, so let me now take you through sulfuric acid. So here's how the problem goes. You've got 10th molar sulfuric acid, that's the given, and the goal is to find out these things I have on the left. The hydrogen concentration, pH, concentration of everything in there. Okay, so I'm going to take you step by step through this. Okay, so first of all, let's look at the chemistry of sulfuric acid for its first acid hydrogen. So its first one's going to come off 100% to give you 1 acid hydrogen, and then you have to write what's left of the sulfuric acid, HSO4, and here's the K sub A for it, infinity. Okay, now the completion step is going to be way, way to the right because it's a very strong acid, so it's going to lose all of the molecules. And notice it's 1-to-1 on the product, so you're going to get the same amount of hydrogen and hydrogen carbonate. So this line here is a summation line. So you have no sulfuric acid. The hydrogen concentration is now a 10th molar, and the same thing on the hydrogen carbonate. Okay, so far that should look pretty straightforward. Now here's where things get kind of tricky. Okay, what is going to happen? We're now going to consider the second acid hydrogen, the HSO4 minus. Now, notice I wrote the start in quotes, and here's the reason why. This is the trick in a polyprotic acid. The start step in acid 2 is the ending on acid 1. That's why I draw these arrows here. So we had 10th molar HSO4 after step 1. That becomes the starting amount in step number 2. That's why they're right over there. So where you ended on step number 1 is the start in step number 2.